Hey, what's up, everybody? Today we're going to talk about graphing and some symmetry. We talked a little bit about x-intercepts and y-intercepts. Today we're going to talk about using these to graph a function. Before we get into that, let's review a little bit about graphing. As you know, we have a plane. We call this the Cartesian plane. It's usually the grid that you see when you need to plot points. Of course, we have our x-axis and our y-axis. There are four other things that you should know about your Cartesian plane, and those are your quadrants. Your first quadrant is in the upper right-hand corner, and then we work counterclockwise around our second quadrant, third quadrant, and our fourth quadrant. The reason we need to know these is they're a good way to identify properties of your particular point. For example, any point within the first quadrant is going to have both a positive x and a positive y value. In our second quadrant, we have a negative x value and still a positive y value. We move down to our third quadrant. We have both a negative x value and a negative y value. And finally, in our fourth quadrant, we have a positive x value, but a negative y value. Now that we've reviewed a little bit about graphs, let's talk about symmetry. There are three types of symmetry that we'll be studying. It's symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. Now, for symmetry with respect to the x-axis, that means our graph is pretty much symmetric across our x-axis. So what does that tell you about your graph? Well, it tells you for every x value that does have a point there, its y value also has negative y plotted there. So if your graph is symmetric across the x-axis, that means both xy and x negative y are plotted on your graph. So let's take a look at an example. This graph right here is symmetric across the x-axis. Is it a function, though? Remember our vertical line test? We can draw lines to see if it intersects more than once, then it's not a function. As we can see right here, this isn't a function. So graphs that are symmetric across the x-axis usually are not functions. But let's take a look at this to see. As you can tell, for every x value up here, like this point right here is at 2, 4. We have another point down here at 2, negative 4. So you can pretty much go at any point along the x-axis where that does correspond with a point on your graph, and its opposite value of its y value is also plotted on the graph. Like we could see 1, 1 is up here, and 1, negative 1 is here too. 2, 4 is here, and 2, negative 4 is there, as well as 3, 9, and 3, negative 9. So if you were to plot a table of the values for your graph, all of your x values would have 2 points corresponding with them, a y value and their negative y value. Now for your first part of your homework, I want you to come up with 2 other examples of graphs that are symmetric across the x-axis. Now that we know how to tell graphically if a graph is symmetric across the x-axis, how can we tell algebraically? Let's say you're just given an equation. How can you tell if it is indeed symmetric across the x-axis? Well, what you do is you substitute negative y into the equation and see if you get the same exact equation. For example, let's look at the equation for a circle that has a radius of 2 and a center at 0, 0. Now, obviously, if we were to plot this, we may be able to tell if it is symmetric across the x-axis, but let's just focus on the equation at hand. Now, if you can recall, the equation for a circle is x minus h squared plus y minus k squared is equal to r squared. Our circle is centered at 0, 0, so h and k are both 0. Our radius is 2, so we plug that over here, and we get x squared plus y squared is equal to 4. Now to test to see if this particular equation is symmetric across the x-axis, what we're going to do is substitute y with negative y. Now we know that any negative number squared is going to be the same as if the positive number were squared. Negative y squared is just simply y squared. So when we plug in negative y, we get x squared plus y squared is equal to 4. That's the same as our original equation. So we do know that this particular equation is symmetric across the x-axis. Let's look at another equation. Let's say we have y equals x. Just the simplest linear equation we could think of. If we substitute negative y in there, we get negative y equals x, which is totally different than our original equation. So the equation y equals x is definitely not symmetric with respect to the x-axis. To wrap this up, go ahead and test and see if the following equations are symmetric, and we'll go over them tomorrow in class.